Hello everyone, welcome to another MCAT ACE lecture, and in today's lecture we are going to be talking about chemical equilibrium. So a general outline as far as what we're going to discuss here. We will first talk about equilibrium theory and concepts. So what does it mean for a reaction to be in equilibrium? What are the requirements? And we'll also take a look at units for equilibrium. Then we'll discuss the equilibrium constant, and we will look at how to actually calculate it, the equation we would need in order to come up with an equilibrium constant. We'll briefly discuss the role of temperature, because temperature is one of the only things that can change the equilibrium constant itself. We will take a look at some sample calculations on how to calculate an equilibrium constant, and then we will briefly talk about the omission of solids and liquids, because a lot of times when we get ready to do these equilibrium calculations, we will typically drop out any solid or liquid states of matter, and that's just because their concentrations seem to be overwhelming in comparison to that of the aqueous forms or the gaseous forms. Then we'll take a look at predicting the direction for reactions. This is probably the type of thing you're most used to if you've gone through a general chemistry course, where we will look at the reaction quotient and compare it to the equilibrium quotient or the equilibrium constant. And when you compare those two, you can determine whether you will favor the reactants or the products at a given time period. Then we'll also take a look at finding concentrations at equilibrium. Now, this is the typical, what they would call an ICE box, ICE, where ICE stands for the initial concentrations, the change in concentrations is the C, and then the E is equilibrium. So you may remember setting up ICE calculations or ICE boxes or things like that in your general chemistry course. They may have been referred to as something else, but we'll take a look at that. We'll look at the general premise of it. You can get into more complicated versions where you have to pull out the quadratic formula depending on the way the equilibrium concentrations are set up. So we'll note that when we get there. Then we'll discuss the theory of LeChatelier's principle. So we're already looking at LeChatelier's principle mathematically speaking in the higher portions of this outline. So at the end we will formally discuss LeChatelier's principle and what happens if I, change the temperature, what happens if I change the pressure, what happens if I change the concentration of either reactant or product, what could I expect as far as the shift in the equilibrium positioning. And then, as usual, we'll have the practice and the summary. So, let's go ahead and get started in our first part of the discussion for chemical equilibrium. So, when we discuss chemical equilibrium, we first want to get a working definition, because we need to understand what we're talking about here. So, as you can see what I've put here, the chemical equilibrium refers to the rates of forward and reverse reactions when they are equal to one another. Now, the reactant and product concentrations are going to remain unchanged with time. So when you think about that, you're talking about the fact that there's not going to be any change in concentration over a long period of time. And if you weren't to disrupt this equilibrium, it would be forever. It could continuously stay in this state. Now, one of the things that students will sometimes get confused with, or they'll have a misconception about, is that this means the reaction has come to completion and that there is no more chemical reaction going on. And that's not true. A chemical equilibrium is in a dynamic state in the fact that you still have products that can be dissociating or reversing back to reactants, and then reactants that are moving to products. And this goes back and forth and back and forth. It's the fact that these rates are now set in stone. And so from the outside, it may appear that nothing else is going on, but there are still exchanges happening at a constant rate going back and forward for the reaction. So if we were to take a look at a general reaction, we could say A plus B. And then remember, if we do equilibrium, we show it with these double reversed arrows here that each have a single head. Goes to C and D. So an irreversible reaction that could not obtain equilibrium, we would just show one double-headed arrow moving to the products. However, this double set of arrows here is suggesting that equilibrium is possible between these two if we were to look at the chemical reaction going on. Now keep in mind, I'm going to put here a little a, a little b, a little c, and a little d in front, because once we balance a chemical equation, we could potentially have constants coefficients that would go in front of these values here. And those coefficients, what I meant to say, would play into calculating the equilibrium constant. Now, we keep bringing up this term equilibrium constant. So when we look at equilibriums, they are characterized or they're governed by the equilibrium constant. And as you would think by the word constant, this is something that will be universal to a given reaction. The only thing that can change the constant is the temperature at which this reaction is taking place. So when we take a look at an equilibrium constant for a specific reaction, provided that reaction is going to take place at the temperature that that constant is given at, so let's say 25 degrees Celsius, then that constant is always going to be exclusive for that reaction. It will not change. Even if you're changing the concentrations, that may shift the products or reactants backwards or forwards, but the constant will remain the same there. All right, so how do you calculate the equilibrium constant? You're going to calculate what's called Kc, and this is abbreviations for the equilibrium constant. And you will do products over reactants. This is the way that we calculate this. So it would be C raised to the little c, D raised to the little d, over A raised to little a, and then B raised to little b. All right, so it's products, and this is important to remember because it's easy to forget, over the reactants. This is the way that you measure your equilibrium constant. Now, this is obviously a general example. We would need to know the specifics of what are A, B, C, and D. However, one of the things that we need to first determine before we even start plugging in individual reactants or products is what is the unit that we are using up here. So the unit that we end up using is typically going to be molarity. So molarity is going to be referring to the concentration when we are dealing with any type of solution. So with solution-based chemistry, when we're looking at reactions occurring in solution, which is most of the time, you have solvent and solutes, you are going to be discussing these calculations in molarity. All right, now if you look here, we typically keep the equilibrium constant itself as a unitless value, and that's because you're going to have molarity at the top, molarity at the bottom. They will cancel with one another when you're dealing with this. So most of the time when we express Kc, it's going to be a value at a given temperature, but we are not going to express Kc in molarity. It's the individual values that are going in that have the molarity there. And then the other way that you could potentially look at this, now I will mention this is a little less common, but it is still very valid, is that you can look at the partial pressure of gases. So you would need gases if you were using this method. Perfectly valid. And if you look at the partial pressure, then you can get the equilibrium constant for the partial pressure of the gases. Now, keep in mind, when you're doing this, Kc, the C there stands for the equilibrium constant based on concentration, so there is a corresponding Kp if I'm looking at it based on pressures. And we will look at this in a few minutes, but it's another misconception that Kc is going to equal Kp. So in other words, it's an assumption sometimes that students make, and this is not true, that the equilibrium constant for the partial pressures will be equal to the equilibrium constant for the concentrations. They are relatable through an equation that we'll take a look at. However, if you were to make this assumption, it's assuming that the concentration of gas is equal to the pressure of that gas. Now, while concentration, because you have mole fraction with partial pressures, while you do have some relationship there, it doesn't mean that the concentration or the moles of gas is directly equal to the pressure, right? So if I had 3 moles of gas, that doesn't mean that that gas is going to exert 3 ATMs on the system. So just keep in mind that this is not a direct correlation. We're going to need some gas law material in order to relate those two to one another. And like I said, we'll take a look at that in a few minutes. But those are the two major units you could use. You could use molarity or you could use partial pressure. Now, I want you to take a note right down here. Changes in concentration will shift the position of the equilibrium state. So this is LeChatelier's principle, and we will discuss this in greater detail later. Okay, but only a change in temperature can cause the constant to change. And remember, the constant that we're referring to here is the Kc or the Kp. So this value itself can only be changed by a change in temperature. So if I change the temperature, I can change the value of Kc. If I change the concentration, all right, so a change in concentration, it will shift this reaction either forward or backwards. There will be a change. The equilibrium state will be disrupted. However, it will reestablish its equilibrium so that it comes back to Kc at a given temperature. So if I keep the temperature steady, again, it may be, say, 25 degrees, and then all of a sudden I dump a whole bunch of reactant B into the system when it was originally in equilibrium, it's going to shift itself in order to reestablish this constant. So LeChatelier's principle would say, well, if I just dumped a bunch of this B in here, I now have too much of the reactants, so it will go ahead and shift towards the products temporarily until it finds the ratio that equals Kc again, and once we've hit Kc, it will reestablish its equilibrium and it'll be good to go at that state. So that's the concept behind LeChatelier's principle. This is a very important concept. You are disrupting the state when you are adding or removing reagents or products like that. However, when you change the temperature, only a change in temperature, can you cause this constant to actually change. And then Kc becomes a different value than it was at 25 degrees. If, let's say, we maybe move it to 50 or 70 degrees. All right? So, one last note here before we move on to look at the constant and the sample calculations in more detail. Okay, physical equilibrium does exist. However, it is not the focus of this lecture topic. So keep in mind, we're talking about chemical equilibrium here. So a good way to relate this, because students sometimes they kind of scratch their heads and they wonder what we're talking about here. When you are discussing equilibrium, there is such a thing as physical equilibrium, but think about physical changes and chemical changes, right? Those are two separate things when we discuss them. Those are two separate types of changes. In one, you're just changing the state of matter. In the other, you're actually changing the chemical identity of the matter. So you have chemical changes and physical changes. The same thing is true of equilibrium. You can have physical equilibrium, for instance, water going from evaporation to condensation, right? Or you could have a chemical equilibrium, which is a different type of reaction. Maybe water becoming hydrogen and oxygen gas. So if I were to take a look at this with the water, I could turn around and say, well, if I had H2O as a liquid, and I put it in some sort of a closed container, right, considering vapor pressure and all of that, it's going to be in an equilibrium between some of that water going into the gas state, that would be evaporation, and then some of it would be condensation and would be going back down to a liquid state. This is an equilibrium, but this is a physical equilibrium because there's no chemical change in the water. It is simply going back and forth between two physical states. So keep that in mind, set that aside as something different. It does exist, but the focus of this topic is chemical equilibrium. All right, so I will go ahead and clear the whiteboard here, and then we will take a look at the equilibrium constant in a little more detail. All right, so now we're going to take a look at the equilibrium constant in a little more detail here. So for starters, remember that the equation we were looking at, the generalized equation before we get into specifics, looked like this. So we had the reactants in equilibrium with the products, where lowercase a, b, c, or d was the coefficient used in balancing the equation, the mole-to-mole ratios, and then the large a, b, c, and d are the identity, the chemical identity of the reactants or the products involved. And we said that Kc, and note that this is at a given temperature, so at given T, because that can change based on temperature, is going to equal the products, okay, and we're going to raise these products to their coefficients, over the reactants raised to their respective coefficients. So if this is the way that I would calculate it, let's take a look at a simple reaction and determine how we would set it up. Now, we're not necessarily going to do numbers yet, although we will get there, but let's take a look at just a general example. So for example, if I had the following reaction, N2O4 as a gas is going to be in equilibrium with 2 moles of NO2 as a gas. All right, now if this is all gas, I could do both partial pressures and or concentration. So let's take a look at how both of those would be set up in a general sense. The concentration, if I wanted to calculate Kc, and we're assuming that this is at some constant temperature, I would have NO2 because it's products over reactants, and I would raise this squared because that comes from the coefficient 2 that I have right there. And then this would go over the N2O4, and that is just by itself there as far as coefficients, so there's an implied 1, so I don't need to do anything to that exponentially speaking. So if I knew what the concentrations were at equilibrium, then I could calculate the equilibrium constant, and vice versa. If I knew the constant, then I could find out what the concentrations of one of these would be. That's where we're eventually going to be headed. Now if I wanted to do it in pressure, the same rules apply. It would be the partial pressure, so P of NO2, and that needs to be squared because we still raise it to the coefficient, and that would be over the partial pressure of N2O4, and that one could just stay how it is. All right, so keep in mind that the Kc is going to be in molarity. Those would be the units there. And then the Kp, when we look at these values here, partial pressure, if you're dealing with gas laws, would be in ATMs. So, if you remember, I did state that Kc is not equal to or equivalent to Kp. And that's really because the concentration of a gas is not necessarily equal to the partial pressure of that gas. So we need to be careful in making assumptions that the Kc and the Kp are interchangeable like that. So how can we relate these? They do have a relatable equation, and it uses gas laws. So if you want Kp to be related to Kc, you're going to take Kp, set it equal to Kc, and when you have Kc, you need to multiply it by 0.821 times temperature. Okay, now that 0.821 comes from the gas law units, and then you're going to raise this to the change in moles. So if you were ever interested at any point in relating the two together, this is the relationship that Kp has to Kc. So this is the gas law, and it's relating moles to pressure. This is actually the gas law constant. It's one form of it. So what we're really going to focus on is writing out Kc. That's what I want people to focus on here. So keep in mind, before we go too much further, there was another thing that I mentioned in passing in the first part of this lecture series, and that's that liquids and solids typically get omitted when we are calculating this. So let's take a look at another equation here. Let's take acetic acid in an aqueous form, and that acetic acid is also going to be present with water. Now usually that's going to be the case because acetic acid as an acid would be in some sort of an aqueous form. So water would be present, and quite a bit of water would be present when you're considering that. All right, so this is in equilibrium with the anion. So we have the aqueous anion plus H3O plus, right? So this would be a weak acid. Remember that weak acids would only partly dissociate. They will not fully dissociate like HCl or anything like that. And so if you have partial dissociation, you typically get equilibriums with a lot of these weak acids. And in fact, when you start calculating equilibrium constants for acids, it's known as Ka. And then you can also have Kb for bases. So that's a whole nother subject, but we have things like Ksp for solubility, Keq sometimes you hear referred to for equilibrium, Ka for acids, Kb for bases. So when we talk about equilibrium constants, they all refer to equilibrium of chemical equations. However, a lot of times you're going to see these separate little subnotes based on what we're dealing with here. So just keep that in mind. If you see something that says Ka, or maybe you've heard of pKa, which is the logarithmic transformation for Ka to talk about acidity, it's really nothing more than the equilibrium of the acid constant that we're talking about there. So the main thing I wanted to get at here is that this liquid, the H2O, is going to drop out when we consider calculating the Kc. So if we were looking at the equilibrium constant, this H2O, which is being used as a solvent here, okay, it's present in quite a large amount. If you were to calculate the molarity of the water that's present as a solvent, it's going to be many, many, many times larger than the other aqueous reactants. So the other aqueous reactants are going to be minuscule in comparison to the overshadowing molarity of the solvent. Now maybe you have methanol as a liquid or something else like that. In that case, again, most of the time you're going to have very large amounts, and so typically speaking, because we don't go in and evaluate them each on a base by base, scenario, you're going to omit liquids and solids here, especially when you see water with any type of aqueous reactants, because if anything's aqueous, it means it has to be dissolved in water, and it's going to be quite a bit of water in comparison to whatever aqueous reactant you have. So what you want to keep in mind here is that if there's no change in the water, then there would be a constant concentration of water. So I don't need to really concern myself about it here. So again, if there is no change in the water, because if I have, let's say, a huge value for the molarity, let's say that I've got something like 55 molarity, right, for the water, and the others are, 1 or less as far as their molarity is concerned. And then let's say that the reaction moves forward, this is the initial state, and then when it's in equilibrium, it's got a molarity of 55.03. That's not really going to be a significant change. So we would consider that the water is constant in that case. And when it's constant and is not going to go through any type of change, then that means that we can omit it from the equilibrium constant. We don't have to consider it when running our calculations there. All right, so that is the equilibrium constant with a couple examples that we've looked at here. So we've talked about the equation. We've discussed the role of temperature. Temperature is the only thing that can change the actual value of Kc. And we looked at some sample calculations. Now, what we're going to want to do is actually look at values now, right, with these sample calculations. And we also just discussed why we omit solids and liquids. So let's go to predicting the direction of reactions. We're going to take a look at QC, which is the reaction quotient. And what QC is it's basically a snapshot before we've hit equilibrium. So we don't call it K, because K is the equilibrium constant, but it's basically an equilibrium constant mock-up at the initial concentration. So when we initially start a reaction is not going to be at equilibrium instantaneously. We have to allow some time for the products and reactants to establish that equilibrium. So we call that the reaction quotient when we get ready to look at initial concentration, and that's QC. So let's go ahead and take a look at how we can do some of these calculations here. So in order to predict the direction of a reaction, let's take a look at another type of reaction here. So for this reaction, we're going to have hydrogen gas, and we're going to have iodine gas. These are going to go in equilibrium with hydroiodic gas. So this is going to be the acidic gas form of hydroiodic acid. So this is going to be at a temperature of, well, we're going to just call it temperature T, all right? And the Kc, so the equilibrium, at some temperature T is going to be 54.3 in this example. So the next thing you need to know is what the concentrations actually are. So in this case, we're going to say that we have 2 moles of the hydroiodic, all right? And we have 0.25 moles of H2, and we have 0.15 moles of the I2. So you have these mole values here. All of these are going to be in a 1 liter container. Okay, now keep in mind what's important here is that these values, once we start plugging them into constants, need to be in molarity. All right? So if you're being given moles, moles is not the same thing as molarity. You need moles over volume. Now in this case, it's kind of easy because we have 1 liter in this case. So if it's 1 liter, any mole value divided by 1 is just going to be that returned mole value in molarity. So we can directly use these values over in the equilibrium. So what we would look at here is we would say, okay, I'm going to set this up. So what would it initially look like? Well, you're going to have HI, and HI is going to be squared. And then you would have H2 multiplied by the iodine. Right? So that's what the setup should look like. Now, because these are initial concentrations that are being given here, we are going to say that this is equal to QC. All right? So, if I calculate this, and you don't always have to have this as initial, it can be at some given time before you've hit equilibrium and you've got the concentrations, but QC is going to be a generic term for when we're not at equilibrium, or we're at least trying to compare to see if we are at equilibrium. So let's plug in these values here. We said we can just use what we were given because the volume of the container is 1 liter. So we're going to have 2 squared over 0.25, right, times 0.15. So if you take a look at this and you were to calculate it, you would have 4 squared, right? I'm sorry, you would have 4. You'd have 2 squared at the top. And then you would follow through with the rest of this, and it would equal 106.6 repeating. So approximately it's going to equal 107, right? So that's the value of QC at this given point in time based on the concentrations. So now the question is the reaction going to move forward or backwards based on the QC value? Well, in order to determine that, you're going to need to compare it relative to the KC. So if you take a look up here, KC was 54.3. QC is 107. So you can start off by saying, well, these are not the same. So therefore, the reaction is not in equilibrium, because if it was already at equilibrium, then the QC that we calculated would be 54.3, and it's not. It's 107. It's much larger than what we would expect the equilibrium constant to be. So what does that mean if we think about it mathematically? Well, if I look at this equation down here, if this is a high value, right, in comparison to what I was expecting for the equilibrium constant, that means that this is too large, right, and this is small, because the value itself is large. So a large value divided by a small value is going to give a high or a large value in return. So what am I really saying in relationship to the equation here? If I'm saying that the large value is on top here, what's on top is the hydroiodic acid in its gas form. So what we're really saying about the reaction in its current state is that there is too much of the HI. So what's going to happen, if I want to predict this reaction, what's going to happen for it to obtain equilibrium? Well, it's going to favor the reverse reaction in this case. So some of the HI will need to dissociate into H2 and I2 in order to reestablish, or to first establish, if this is on its way to, the equilibrium constant. So I need to produce more of these guys in order to get to Kc. And that's how I can predict the direction of a reaction. I can take any time, as long as I'm comparing relative temperatures to one another. Okay, I can take at any point the concentrations and I can find what Qc is. If I know Qc, I can compare it logically to Kc, and then I can determine whether I'm at equilibrium or I need to shift one direction or the other to establish that. So let's make ourselves a nice little reminder down here in relation to that. So what happens if Qc is going to be greater than Kc? Well, in a case like that, we would favor a forward product-driven reaction. Okay? So if you think about what this is saying, it's saying Qc is too low, it's too tiny. That numerator, where the product is, needs to get larger in order for it to hit what Kc should be. So therefore we need to move forward, we need to drive towards the products. This all relates back to LeChatelier's principle as far as driving back and forth. Okay? Now, the next thing we could say is, what if Qc is equal to Kc? Well, in a case like that, then we are at the equilibrium. And if we're at the equilibrium, we don't need to worry about which way the reaction is going to move backwards or forwards, because it already has that dynamic established. And then, when we have Qc, and this is what we just saw, being greater than what Kc is, then we're going to have the reverse reaction favored, so it's going to be a reactant-driven movement, meaning that the reaction will drive backwards or go in reverse until the appropriate amount of reactants have been created in order to establish what Kc should be. So that is the equilibrium constant and how we can predict which way a reaction is going to move at any given time if we can compare it to that equilibrium constant, right? And most reactions will have an equilibrium constant determined at any given point. In other words, once the reaction has been discovered and characterized, it's relatively easy to go in and determine the concentrations, through assays or other things. And so once equilibrium has been established over a course of time, a lot of these values you can find in literature, you can pull out. So you could always get the Kc and reference it. Now sometimes you may need to be able to determine what Kc should be, and in that case that's what we're going to start to take a look at next, which is finding, if you're at an equilibrium, finding the concentrations that are required at that equilibrium. So that's what we're going to do. Allow me to just erase the board here, and then we will take a look at finding equilibrium concentrations based on that type of state. Okay, so now we're going to take a look at finding equilibrium concentrations and the math that goes into that. So let's take a look at the same reaction we were just working with, since we're familiar with it. So we've got the H2 gas plus the I2 gas, and that's going to be in equilibrium with the HI, and that's gas as well. So this needed a 2 as far as balancing was concerned, and we will go ahead now and take a look at how to solve for this. So let's say that we start this reaction off, and when we get ready to start it, as far as the initial setup, right, I shouldn't have any HI when I'm working with this initial setup here. So I get some H2 and some I2, and I'm going to add them into the vessel. So to keep things simple for right now, we'll also look at a 1 liter vessel. So that's going to be the volume involved here. And let's say that I have 0.75 0.50 moles of each. So that's, I have that much H2, and I also have that much I2. All right, so those are the initial concentrations, and again, if it's 1 liter, you can equate this to the molarity in a case like that. So I'm going to look at the initial values, then the change, and then I need to look at the equilibrium itself in order to set something like this up. All right. Now, keeping in mind that the Kc we said for last time was that at a given temperature, the Kc value here is going to be 54.3. So let's keep with that. That'll be what Kc is supposed to be equal to. And then we will go ahead and get ready to start solving this. So this is where I mentioned the ice box. So I'm going to just move this over here so we have some room. Okay. So when I get ready to set up my ice box, I start and I say here's I, C, and E. And remember, I stands for initial, C stands for change, and E stands for equilibrium. So what are the initial values that I have here? Well, I said that I was going to start with 0.750 H2, 0.750 I2, and then there's 0 HI at the very start of this reaction. So what can I expect for the change as I'm headed towards the equilibrium constant? Well, now what I want to look at is the general ratios of these. So a mole to mole ratio, right? So what I'll say is that for every 1 mole, I'm going to set that equal to X. That's how I'm going to work with this. So what would I expect? Well, I would expect that for every 1 H2, I would lose that on the way forward to creating HI, and I would lose 1 I2, and then I would form 2 HIs, right? So if I've got 2 of them, it's 2X, not just 1X. And that's based on, again, these values here. I've got 1, 1, and then a 2, most importantly, right there, right? So the change after this reaction is up off the ground and running is that I would need to lose some of the hydrogen and iodine in order to create some of the hydroiodic acid. And the only way that I can do that is by depleting some of the reactants and moving them to some of the products. Now, this is not a full forward reaction, right, because it's in equilibrium. So this is not an irreversible, we create nothing but HI and we're good to go. So then I need to look at the equilibrium. You can almost look at this as a math equation here. So then, if I look at what I have here, at equilibrium, I have 0.750 minus X for the H2. And then I also have 0.750 minus X for the I2. And then I would have 2X for the HI. Now think about this. Does this make sense? Well, this should not go down to 0, right? Because if it's an equilibrium, it means that there is at least some amount of H2 and some amount of I2. So the amount that's there is the initial amount minus the amount I lost in order to drive the reaction over to HI. So this should not be 0. It should be 0.750, the initial amount, minus however much I lost during that change phase. Same thing for the I2. Now, should this have a numerical value other than the 2? Not at this point. We have to figure out how much of it actually formed, and what we're going to have to figure out here is X. We're really going to solve for the change after we've gone from initial state to equilibrium state, right? And then whatever X is, if I multiply it by 2, then that's what the HI should be at equilibrium. So moving forward, now that I have these values, I'm going to set up the equilibrium constant and set it equal to the values that I have here. So, what is Kc? Well, we said we're going to set Kc equal to 54.3. So let's do that. 54.3 equals, now we want the equilibrium constant equation. So that's going to be the HI squared over the H2 times the I2. Let's plug in the actual values here. So HI is going to be 2X, right? So come back up here, just so everybody's following, 2x. That's what we represent HI with at equilibrium. And because it's squared, because we have a coefficient of 2, so we need to make sure that we have that in there. Then the products are going to be 0.750 minus x, right, times, okay, or you could square this, 0.750 minus x. Now the reason I wrote 2 of these out and I didn't square it here specifically is so that people didn't get confused and think that I was pulling a 2 from either of the coefficients like I did up here. Okay, so while you could write this squared, and it would work in this case, you need to keep in mind that that squared is simply because of the coincidence that these were both at the same concentration and would have had the same loss here. So they're identical to one another in this reaction. There would be many other reactions where you could not do an example where you just simply square it here, right? For instance, if I had different starting concentrations, at that point each of those is going to be their own set there. Alright, so now what would I need to do in order to move this forward? Well, I'm going to have to get rid of the squared value so I can start solving for x. So the way that I would do that is by taking the square root. So I'm going to need to take the square root of this side, and I have to take the square root of this side, because algebraically, whatever I do one side, I have to do to the other side. So the square root of 54.3, if you were to ballpark it and estimate it, 49 would be 7, right? But we're not as high as 64 for 8. So in this case, it turns out that it's about 7 1/3. So it's technically 7.37. But if you could get somewhere in that ballpark, then you'd be good as far as estimating numbers. So then that equals what? 2x, because we've removed the squared value. And then we would have dropped one of the 2 values at the bottom because they are the same. Now, again, this could get more complicated if those 2 were different, and then you'd have the square root of each of those values. So 0.750 minus x. So at that point, this has become much easier. We can algebraically solve for this by simply multiplying the numerator. Multiplying the denominator over to both sides so it cancels out, distributing, and then dividing through by 2 in order to find your x when you algebraically shift it around. So maybe you should pause it and attempt to do that for a minute. Okay. And if you were successful, you should have gotten approximately 0.6. So it would be 0.590 molarity. So are we done at this point? Well, this is what x is equal to. So if I wanted to really find the concentrations at equilibrium, I would need to go in and I would need to plug these values back in order to find those equilibrium values. So in other words, I know what x is, but if you look at equilibrium here, right, let's highlight this in a different color. If I look at equilibrium, these concentrations are not just equal to x, right? I have to plug them in. So this is really the more simplistic part. I just have to plug x in and figure out what it is. So for H2, right, H2 concentration at equilibrium is going to be 0.160 molarity. Okay, that means that I2 would also be the same. Right, now where is this number coming from? Well, all I had to do was turn around and say, at equilibrium, H2 and I2 are going to be 0.750 minus x. So I just take 0.750 minus 0.590. That equals 1.6. Okay? And then the HI, the concentration of HI at equilibrium, right? We got to remember that we're doing a times 2 multiplier here, so it would be 0.590 times 2, and that's going to be 1.18 molarity. All right, so as I noted, sometimes the quadratic formula needs to be utilized here. And if that's the case, it's going to require some more work to basically frame your equilibrium as far as the x squared plus x plus the value, and then put that into the quadratic formula and solve for the x using that. So it is possible. It's certainly, there are examples you can go through and find in analytical chemistry books, or probably even in some Gen Chem books. But note that if you can't solve it the way it's currently set up, it's most likely that you'll need to utilize the quadratic formula in a case like that. So now that we've seen an example that we've walked through with this, let's discuss the theory of LeChatelier's principle, and then we will get ready to start some of our practice here. All right, so now we're going to look at LeChatelier's principle in theory. And this will sort of conclude the lecture on the equilibrium constant and chemical equilibrium itself. We will move over to the practice problems and the summary of what we learned after that. So when we look at LeChatelier's principle, there's a couple of things that we could add or remove in order to change how the state of the equilibrium is going to behave. So let's go back to one of the first reactions we looked at, and that is if we have N2O4 as a gas, and that is in equilibrium with 2NO2. All right, pretty simple equation. And it's good because it also has this squared multiplier for the product, which will help us in understanding some of what's going to come in this LeChatelier's principle discussion. So first and foremost, added concentrations will shift the equilibrium away from the added reagent. Removing concentrations will shift the equilibrium towards the removed reagent. So arguably this is going to be the most simplistic of all the discussions that we have here as far as seeing it conceptually in your head. So let's look at the first one. An added concentration will shift the equilibrium away from the added reagent. So this reaction right here, it's currently in equilibrium. And let's say that I come in and I say, I'm going to dump a whole bunch of N2O4 gas into the vessel and see what happens. Well, if I disrupt the equilibrium by adding N2O4 gas, it's going to get rid of some of it in order to reestablish the equilibrium. It now has too much of the N2O4. So what does that do? It drives the reaction forward in this case. So look at what we just said. An added concentration will shift the equilibrium away from the added reagent. So I added N2O4, and therefore I'm going to shift this away from the N2O4 and drive it towards the NO2. All right, now the reverse is true. I can also remove the concentration, and it will shift the equilibrium towards the removed reagent. So let's say that this is in equilibrium, and somehow I manage or find a way to remove some of the N2O4 gas. Well, in that case, when I disrupt the equilibrium by removing, it is going to shift towards the removed reagent, right? So in this case, I've gotten rid of some of that initial reactant. That disrupts it, and the equilibrium constant says, hey, I need some more of the N2O4. It was just taken away. So in that case, the NO2 will combine together in order to make some of the N2O4 that's required to maintain that equilibrium state. So again, this is probably the easiest one to grasp conceptually. Now the other ones aren't horribly difficult, but it requires a little more thinking when you look at it. All right? So what happens if I'm going to increase pressure or decrease pressure? So we'll look at increase, and then the reverse is true for a decrease here. All right? So if I increase pressure, this will increase the concentration of reagents because the volume is going to be restricted. So this will have an exponential effect on the higher coefficient reagents. So let's take one step at a time when we're looking at this. I have some vessel with the reagents, right? And let's say that I have some sort of a piston here that I can move up and down. So here are the gas reagents. They're hanging out in here. They have a certain volume that they occupy. If I increase the pressure, which is going to decrease the volume, right? So now I take a look at this again, and let's say that I brought the piston down here. Now all of a sudden, there's a lot less volume to hold all of these reactants and products. And so what I'm effectively doing is I'm increasing the concentration, right? Because there's less volume for them to occupy at that point. So if I increase concentration, meaning I've added concentration, it will shift away from the added reagent. Well, if it's all a 1-to-1 ratio, that's fine. It's really just that everything has become more concentrated and it equals out. But that's not always going to be the case. So in the case of the N2O4, right, looking at this reaction that we had up here, remember that the way the equilibrium constant would be set up is that I would have NO2 squared over the N2O4, right? So if the pressure, let's say, is going to increase to the point that it doubles the concentration, so let's say that this was 1 and this was 1, then all of a sudden, right, this becomes 2 and this becomes 2. Well, this becomes 2 squared, which is 4, whereas this just stays as 2, right? So what you have to keep in mind here is that there's going to be a larger effect on the concentration for those that have the exponential multipliers. So if the pressure is going to increase, it will increase concentration, and it's going to disproportionately increase this squared value because of that multiplier. So what would be the end case here? We would see that NO2 would, or the concentration of NO2 is going to see a greater increase than that of the N2O4, and so it's going to shift the equilibrium towards the reactants, right? So the N2O4 is on the reactant side. If I come back up and I look at this equation, what I'm saying is the increase of pressure is going to greatly increase the concentration of this guy in comparison to this guy. So if this one has the higher increase, or the added concentration, then we shift this way, right, to the reactants in order to accommodate that. So again, the pressure-volume relationship, which is an inverse relationship, can have an effect on the concentrations and therefore can shift the state of the equilibrium back and forth. Now, heat, and remember that temperature change can actually change the value of the equilibrium constant itself. Heat will drive an endothermic reaction forward, but it will reverse drive an exothermic reaction. So it'll start going back to the reactants. So the way to look at this, okay, again, we can utilize the equation that we had before. So if I have N2O4 gas, all right, and this goes over to 2NO2 gas, you would need to have a little bit of your thermochemistry in order here, which is to say that you need to figure out if your delta H is going to be positive or negative, because that's going to tell you if it's endothermic or exothermic. Well, in the case of this reaction, the reaction would be 58 kilojoules per mole, and that is plus 58 kilojoules per mole. So remember that if delta H is going to be positive, then it's an endothermic reaction, and if delta H is negative, it's going to be an exothermic reaction. Right? So what I need to take away from this is the fact that this right here shows me that this is an endothermic reaction. So what does that mean? It means that heat must be absorbed as a reactant with the N2O4 in order to drive the reaction this way. So if heat is considered a reactant because it's endothermic, right, then if I increase the heat, that means I'm increasing one of my reactants. You can view it almost like a chemical reagent, and that drives the reaction forward. Okay, so heat will drive an endothermic reaction forward, but it's going to reverse drive an exothermic reaction. Right? So what happens if, let's say that I had some reaction, we'll just put A and B, right? So A goes over to B, and in this case the delta H of this reaction, and you could even show the reverse reaction here if you wanted to put NO2, right, and N2O4 over as B. But let's say that I have a reaction where it's negative 58 kilojoules per mole. Well, in a case like that, if I were to add heat, what this is saying is that once A dissociates into B or becomes B, it will also release some heat because it's exothermic. So heat is a product in this case, right? An exothermic reaction releases or generates heat. So now if I increase or I heat the reaction, that is going to reverse drive this, because I'm saying as I add heat, I'm really adding a product, and so the reverse of this reaction is going to be favored in this case. So that is how heat and temperature works as far as the LeChatelier principle and shifting the equilibrium state. All right, so that finishes the content that we want to deliver for the chemical equilibrium series. So I will go ahead and I will pull up the practice questions. We will practice those, talk about our summary, and then we'll be good to go for chemical equilibrium. So give me a moment to bring the questions up, and then we'll get started on those. All right, everybody, here are the questions that we are going to practice for the chemical equilibrium lecture. So to get started, I want you to consider the first equilibrium reaction that I've shown up here, which is the PCl5 gas is going to decompose into PCl3 and chlorine gas, Cl2. Now note that the enthalpy is given here. So we know that this is going to require 92.5 kilojoules per mole, because remember that plus is going to represent an endothermic reaction, so that might be important here. And then if you look at question 1 and 2 are both going to deal with this reaction. Question 1 says, which of the following would promote a shift in the equilibrium state towards the reactant? So we're looking for a left moving or a reverse equilibrium state. This is really nothing more than evaluating LeChatelier's principle here. You don't have to do any math per se, but just evaluate what would happen based on each of the following options in that question. Then number 2, we are going to bring some math into it. So I figured for this question we would try one of the calculations with partial pressures, since we did a lot with the concentration throughout the lecture series. I wanted to give you a little exposure to that. So find the partial pressures for the Cl2 gas if these gases are placed in a 1 liter vessel with the following pressures. So again, we're referring to this reaction up here, and you're going to calculate the partial pressure for the chlorine gas given the other conditions here. And here are the conditions. The partial pressure for the PCl3 is 3.00 atms, and the partial pressure for the PCl5 is 2.00 atms. Right? And then Kp, which is going to be the equilibrium constant pressure-based, is found to be 2.50 under these conditions. Now we're assuming a steady temperature when we're doing that. That's what under these conditions is referring to. Okay, so you have a couple options there. Which of those would be the appropriate partial pressure for the chlorine gas given the other partial pressures for the other reagents involved in this equilibrium? All right, so now going down here, I have another equilibrium to consider. So take a look at this. You've got nitrogen gas and hydrogen gas. Those are going to combine in order to give ammonia gas. Now, for the third question here, which is referring to this reaction, we're going to calculate the reaction quotient. So remember, that's QC, all right, at a given time if the following conditions are known. All of the reagents are placed in a 2 liter container. Keep that in mind, that value is important. Okay, at 375 degrees Celsius. There are 2 moles of nitrogen gas, there are 4 moles of hydrogen gas, and there are 5 moles of ammonia gas. So the question is, given those conditions, all right, what would the reaction quotient be? So you're calculating QC for this problem. And then here's part 4. Given that the accepted Kc of this equilibrium is 1.2 when the reaction vessel is at 375 degrees Celsius, which is what it was in the problem above, predict what will happen given the current state of the reaction in question 3. So this is saying, look, here's all the information in part 3. You are evaluating where the equilibrium is going to lie relative to the actual equilibrium constant. So up in part 3, you're calculating the QC, and then what you're doing here is you're attempting to compare the QC to the KC in this part. So that's what we're going to shoot for, and I will go ahead and scroll through this one more time so that you can pause and take notes if you need to. and then we will go ahead and practice it afterwards. Alright, so let's go ahead and evaluate these questions. So, we're considering the first equilibrium for part 1, and it states which of the following would promote a shift in the equilibrium state towards the reactants. So, the goal here is that we want to find one of these conditions that's going to promote the reaction shifting or moving in this direction right here. So we're looking to produce more of the PCl5 gas when we look at the condition that's going to meet that. So, which of the following would promote that shift? The removal of PCl3. Well, PCl3 is one of the products here, so if I remove that, removing the product is going to drive the reaction forward to produce more product. So that is going to be a move towards the product side, not the reactant side. So that one's going to be out. All right? The addition of heat. So in order to evaluate this, I need to see is this going to be endo or exothermic. Now, if you're paying attention, we said that this is endothermic. You should be able to gather that from the fact that this is a positive kilojoules per mole value for the enthalpy. Now, what does that mean? It means that heat is required in order to move this reaction and drive it forward. So heat, you can be viewing heat as a reactant in this case. So the addition of heat is going to push this forward. It's going to move it this way, right, if it's endothermic. And so again, that would not be the option that we're looking for because that's going to produce more product-driven behavior. What about the addition of PCl5? So if I'm adding PCl5, which is one of the reactants, well, this again is not the option that I want, because if I'm adding more of the reactant, LeChatelier's principle says there's then too much of that, so it will disrupt the equilibrium, again moving it forward towards the products in order to help even it out and reestablish the equilibrium state. So that leaves me with D as the only option. Now, does D actually make sense? The addition of Cl2. So just the opposite of what we saw with the reactants. If I add additional product, there is then too much Cl2 and it will shift to the left in order to compensate for that and reestablish the equilibrium. So yes, option D is indeed what we are looking for there. Alright, so for question 2, it says to find the partial pressure of Cl2 if the gases are placed in a 1 liter vessel with the following pressures. The partial pressure for the PCl3 is 3, the PCl5 is 2, and Kp is going to be found to be 2.5 under the given conditions. So what I really want to set up here is my Kp equation. Now, it's products over reactants. So the products that were found here are going to be the Cl2, the PCl3, and then we also have the PCl5, that's the reactant, so that's going to go at the bottom. So the way that I would set this up, if I was looking at it, is I would say I have the pressure of Cl2, and I'm going to have the pressure, right, these are the partial pressures, of the missing the P there, PCl3, right? And all of this would go over the pressure of the PCl5. All right. So what values do I know? I know Kp is supposed to be 2.5 under these conditions. I'm looking for the PCl2, so that's going to stay there. Right? And then I'm going to have the PCl3. The PCl3 is 3 ATMs. Right? And then if I come down here, the PCl5 is going to be 2, according to this. So if I move forward with this, and I were to algebraically rearrange this and solve for it, you should have found that the PCl2, I'm sorry, let's keep that as a subscript there, so it doesn't look like phosphorus. So the pressure, the partial pressure of the Cl2 is going to be equal to approximately 1.66. And that's answer C. So answer C should have been what you got, and this is the mathematical way to work through that with the pressures and the Kp that's given. All right, consider the following equilibrium. We have the nitrogen gas and the hydrogen gas, and that's going to be in equilibrium with the ammonia gas as the product. So we're going to be doing a sort of a similar type of setup to what we just did in 2. Now keep in mind that in this case this is not Kc or Kp. We're looking at a Qc that we're going to calculate because we're looking for the reaction quotient at a given time. And there's a couple important things here. 2 liters, right, means that I need to have these values, because if it's 2 liters, then that means that the volume is 2 in comparison to a lot of these other examples where we had 1 as the volume. So the way that I would set this up then is that the QC is going to be equal to the NH3, and that would be squared because of the coefficient of 2 associated with the balanced equation. I'm then going to have my H2, and that would be cubed, again due to the coefficient, and then I would also have my nitrogen gas. So this would be the setup for the quotient that I'm looking to calculate at this given time t. Right? Now this really isn't so important in this particular case, but the reason this is in here is because every single Kc is unique at a given temperature. And so in the next problem, if we're going to compare Kc, we need to know the temperature that that Kc is at in order to make the proper comparison here. So this is just sort of side info that's in there. All right? So now, if we take a look at this, we can actually fill in the values and we should be good to go. But remember, we need to cut these guys in half. Right? And that's because of the volume being 2. So when you get ready to set this up, if the NH3 is 5 moles, then that would make it 2.5. It would be 2.5 squared. Okay, and then the hydrogen gas would be 2 because it's really 4 when we're looking at it. So this would just be 2. And that 2 is going to be cubed. And then the 2 divided by 2 for the nitrogen is just going to give us 1. So if we simplify that, we're going to find that QC is equal to 2.5 squared over 8, and that is going to be approximately 6.25 over 8. And so when we look at that, that is roughly 0.8 if you're following along. So the closest answer and the correct answer if you were to plug this into a calculator would be A. Okay, and the rest of these guys would drop out. Now, given that the accepted Kc, so this is the actual value if this reaction were to be in equilibrium, at 375 degrees Celsius, it's 1.20, right? So this is the value I need to compare to the value I just got up there. So predict what will happen given the current state of the reaction in question 3. So I can actually take this value and I can say, let's look at the 0.781 in comparison to the 1.20. Is this greater than, less than, etc.? So this would be less than 1.20. And therefore, we know that if we have a QC that is going to be less than a KC, we need to move the reaction forward, right? Because we have to increase the numerator, and the numerator is the product. So it would be a forward-driven reaction. So the best answer here is going to be B. The reaction will be forward-driven towards the products. Because as we drive it towards the products, remember the products are up in the numerator, the value gets larger, the quotient gets larger until it hits 1.2, and at that point you would have the Kc and the Qc equal to one another. So B would be the best option here. All right, so that is it as far as the example. So hopefully this gave you a good sampling of the types of equilibrium calculations and theory that you could come across related to chemical equilibrium. So what I will do now is clear the screen here. We'll bring up the summary just to go over one more time everything we've discussed, and then we will move forward and conclude. Okay, so here's the summary for everything that we learned regarding chemical equilibrium in this lecture. So first of all, remember the definition of chemical equilibrium. We're talking about the forward and backward rates of these reactions being equal to one another as far as their exchange and their rates. So another way of framing that is to say that there will be no change in concentration for the reagents over time. And that's a good way of framing chemical equilibrium. Now remember that chemical equilibrium is different than physical equilibrium, and we did take a note about this where we said something with physical equilibrium, for instance, would be water in a closed container. It's going between that liquid and gas state with evaporation and condensation cycles. That is a physical change in the water. That is not a chemical change. The water has not changed its actual chemical identity in a case like that. So we define the equilibrium state by a rate constant, an equilibrium rate constant, and that equilibrium constant is going to be set at a given temperature. So we can change concentrations, and that will disrupt or shift the state of the actual equilibrium, but it's not going to change the value of the equilibrium constant. Only a change in temperature is able to do that. And keep in mind that we can evaluate the equilibrium constant as Kc, which is for concentration, or Kp when we're dealing with partial pressures if we have gases involved. And when we get ready to look at that, you can use either of those, and they would both be acceptable. But remember, we did discuss that Kc is not equal to Kp. We have to relate the two through a gas law equation using moles and the gas law constant. Now, when we talk about the actual equation for Kc, and the same would apply for Kp, the way that we would define it is that it's products over reactants, and so we saw several reactions where it was A plus B and C and D, and so we said the products, C and D, would be on top, and then the reactants, A and B, would be at the bottom. So these are all the reagents, the products and the reactants, and then they are raised respectively to the exponential power of whatever their coefficient is. So remember, the coefficients that come from the balanced equations are going to be used to exponentially raise the values of these concentrations. Now, we discussed the reactant quotient, which we abbreviated as QC. This is similar to Kc, however, we're taking that at a time t, and we're trying to see how close we are to equilibrium. So there is a potential that QC is actually equal to Kc. However, most of the time it probably has a shift in the reaction before it would obtain the actual value of Kc. So when we determine these concentrations at some given time t, we plug it in just as we would with Kc, we call that QC, and then we compare it to Kc to determine the reaction progress. Is it at equilibrium, or does it need to shift one way or the other? So if the QC is less than the Kc, it's going to be a forward-driven reaction that favors product formation. If the QC is equal to the Kc, at that point we're at equilibrium and there would be no effective change. And then finally, if QC is going to be larger or greater than Kc, that would be a reactant-driven process, and the reverse reaction is going to be favored in that case. Now keep in mind, along with QC, we talked about being able to determine the concentrations of reagents if we know the Kc value. So this was the ICE method that we used, where ICE stands for initial, change, and equilibrium. So the initial was however much of the given reagents, so specifically the reactants we started with, and the product should be 0 at that point because the reaction is just initiating, it hasn't started. Then we looked at the change, and based on the coefficients that were there, we saw that that can affect the amount of X, quote unquote, that we use when we're determining change. And then we subtract that X from the reactants, we add it to the products, and we determine the equilibrium when we set it up by plugging X in to these concentration values. And then we solve for X mathematically. Keep in mind we may have to use the quadratic formula in some of those cases if they become a little more complex as far as solving them. We finally wrapped up by discussing the general concept of LeChatelier's principle, and as an overview of that, if you add reagents, you are going to shift the reaction away from that reagent that you added. So it's going to, let's say we add a product, that is going to move the equilibrium away from the products and drive it towards the reactants until it reestablishes that equilibrium state. Okay, so if we remove any reagents, we are going to shift towards the reagents that we have removed. For a change in pressure, that one's a little bit trickier. We have to evaluate the effect that that change in pressure had on the concentration. So specifically, if some reagents are going to be squared or cubed or to the fourth power based on their coefficients, those are going to see a greater change in concentration when we have the pressure changing. So remember, for instance, if pressure increases, the volume decreases, so that would be an overall increase in concentration because the volume is decreasing. So when you have a situation like that, you need to determine if they're all being doubled in concentration equally, or if some of them are going to have exponential multipliers, which means their concentration will be much larger and therefore move away from those reagents. It takes a little bit of evaluation there. So then finally, when we get to temperature change, we have to look at the heat, and if heat is going to be added, if it's an endothermic process, that's going to be a forward-driven reaction, so that'll favor the products, because the heat would be considered one of the reactants in an endothermic reaction, and then the opposite is true for the exothermic. So in an exothermic reaction, if heat is added, then it's going to favor the reverse back to the reactants. So that pretty much covers everything we needed to discuss for chemical equilibrium. So this has been an MCAT ACE presentation on chemical equilibrium. Thank you for taking the time to learn with us, and we will see you for future lectures.